Maps of the Pacific Northwest often create the impression of permanence. Towering forests, rugged coastlines, volcanic peaks, and broad inland valleys appear fixed against the horizon, as though they have occupied exactly the same positions for countless generations. Yet every hour of every day, the landscape is quietly changing shape. The transformation is so slow that no person can witness it directly, but the evidence has become impossible to ignore. Highly precise scientific instruments anchored into solid bedrock have revealed that portions of the Pacific Northwest are gradually tilting, with some areas steadily rising while others slowly sink. The changes are measured not in feet or even inches each year, but in mere fractions of an inch, equivalent to only a few millimeters annually. Although almost imperceptible over a human lifetime, these movements accumulate year after year, century after century, gradually reshaping an entire region. Far from being a sign of surface instability, the tilting reflects forces acting many miles below the landscape. The Pacific Northwest occupies one of Earth's most active tectonic environments, where the Juan de Fuca plate relentlessly converges with the much larger North American plate. This collision has continued for millions of years, storing immense amounts of mechanical energy within the crust. Instead of producing continuous dramatic earthquakes, much of that energy is absorbed through slow deformation. Rocks flex, coastlines rise, valleys settle, and entire regions gently warp like a massive wooden beam bending under an invisible load. Modern science has transformed these subtle movements from theoretical concepts into measurable reality. Continuous Global Positioning System stations, commonly called GPS stations, monitor fixed locations with extraordinary precision. Rather than simply helping drivers navigate roads or hikers find trails, these scientific instruments can detect crustal movements measured in fractions of an inch, equivalent to mere millimeters. Every observation contributes to a growing record showing that the Pacific Northwest is not behaving as a rigid block. Instead, different sections move at different speeds and even in different directions, creating a slow but measurable tilt across large portions of Oregon, Washington, and Northern California. The process begins far offshore along the Cascadia Subduction Zone, a tectonic boundary extending for roughly 700 miles, or approximately 1,100 kilometers, from Northern California to British Columbia. There, the dense oceanic Juan de Fuca plate moves steadily toward the continent before descending beneath the North American plate. Although the average convergence rate varies along the boundary, it generally approaches approximately 1 1/2 to nearly 2 inches per year, equivalent to about 4 to 5 centimeters annually. That pace may appear insignificant until viewed through the lens of geological time. Over centuries, the accumulated movement reaches many yards. Across millions of years, it has constructed mountain ranges, uplifted marine terraces, and generated some of Earth's largest earthquakes. The interaction between these plates does not resemble two smooth surfaces sliding effortlessly past one another. Instead, friction causes sections of the boundary to lock together. Imagine placing one hand beneath a heavy rug and attempting to push it across a floor. The rug refuses to glide smoothly because friction holds portions in place. Pressure builds as the hidden hand continues pushing. One area bulges upward, another wrinkles, while another bends gently before finally shifting. The Pacific Northwest behaves in much the same manner. The crust is not moving as one solid sheet. Instead, it flexes continuously under forces generated deep below the coastline. That continuous flexing explains why the region experiences different patterns of vertical movement depending upon location. Scientists studying decades of PS observations have identified a remarkably consistent picture. Along the western Olympic Peninsula in Washington, the land is rising at an average rate of roughly 4 to 5 millimeters each year, equivalent to approximately 0.16 to 0.20 inches annually. That amount is thinner than the thickness of several stacked coins, yet over 100 years, it becomes approximately 16 to 20 inches, or about 40 to 50 centimeters. Extend the same process across 1,000 years, and the accumulated uplift exceeds 13 to more than 16 feet, equivalent to roughly 4 to 5 meters. Travel only a relatively short distance eastward, however, and the pattern changes dramatically. Southern Puget Sound behaves differently. Instead of steadily rising, portions of this region slowly subside. The downward movement remains small from year to year, yet it demonstrates that neighboring regions are responding differently to identical tectonic forces. The crust resembles a giant flexible platform rather than a rigid slab. One side arches upward while another settles downward, producing the gradual regional tilting now documented across the Pacific Northwest. Central Oregon introduces yet another pattern. GPS measurements indicate relatively little vertical uplift compared with coastal Washington. The crust there appears considerably more stable in terms of elevation, suggesting that deformation is distributed differently depending upon local geology, crustal thickness, and proximity to the locked subduction interface offshore. Continue traveling farther south toward Northern California, and measurable uplift begins increasing once again. The landscape starts rising after passing through regions that had previously shown comparatively limited vertical change. Viewed together, these observations reveal a landscape behaving almost like a slowly flexing bridge. One end rises while another dips, creating broad regional warping extending across hundreds of miles. Individual residents may never notice these changes during their lifetimes because the annual movement remains astonishingly small. Scientific instruments, however, never lose patience. Day after day, year after year, they quietly accumulate millions of measurements until unmistakable long-term trends emerge. Long before satellites orbited Earth, geological evidence hinted that similar processes had operated for far longer than modern observations could reveal. Ancient marine terraces preserved along portions of the Pacific coastline record repeated episodes of uplift spanning hundreds of thousands of years. Former shorelines now stand high above present sea level, indicating that the land itself gradually rose over immense spans of geological time. Elsewhere, buried sediments and coastal deposits preserve evidence of alternating uplift and subsidence associated with repeated tectonic cycles. These ancient records demonstrate that modern GPS observations are not capturing a temporary anomaly. They are documenting an ongoing tectonic process that has shaped the Pacific Northwest throughout much of its geological history. Today's measured tilt represents merely the latest chapter in a remarkably long sequence of crustal deformation. Scientists studying crustal deformation often describe Earth as possessing elastic properties. Rocks appear rigid during everyday experience because they resist bending over short periods. Under continuous stress, lasting decades, centuries, or millennia, however, they behave differently. Entire sections of the crust slowly flex without immediately fracturing. The deformation resembles the gradual bending of a thick wooden board under sustained pressure. The board remains intact while storing energy internally until eventually reaching its mechanical limits. The Pacific Northwest currently exists within precisely such a phase of slow elastic deformation. Offshore, the Juan de Fuca plate continues pressing eastward beneath North America. Since much of the plate boundary remains locked by friction, neither plate can move freely. Instead, stress transfers into the overriding continental crust, gradually bending it upward in some locations while depressing it elsewhere. This explains why the measured tilting does not occur uniformly across the region. Geological structures differ from one location to another. Variations in crustal thickness, fault geometry, rock composition, and the exact position relative to the offshore plate boundary all influence how deformation spreads inland. Rather than forming a perfectly even slope, the Pacific Northwest develops a complex mosaic of uplifting ridges, slowly subsiding basins, and gently bending transitional zones. Researchers compare thousands of GPS observations collected across extensive monitoring networks. Every station serves as a fixed reference point, anchored securely into stable rock. Satellites repeatedly determine each station's position with extraordinary precision. Tiny annual shifts accumulate into measurable trends that reveal regional deformation patterns invisible through ordinary observation. When visualized on scientific maps, the results resemble flowing contours rather than rigid blocks. Vectors point toward ongoing motion, while color gradients illustrate differences in vertical change. The entire region appears alive with slow movement, despite seeming completely motionless to anyone standing upon it. One remarkable aspect of these observations lies in their consistency. Individual measurements might contain slight uncertainties, but years of continuous recording reduce random variation until clear regional behavior emerges. Independent research groups using different analytical methods have repeatedly reached similar conclusions. Coastal uplift, inland subsidence, and regional tilting consistently appear across multiple datasets. The deformation also affects infrastructure in subtle ways. Engineers designing long-term projects such as bridges, ports, pipelines, and coastal facilities increasingly incorporate geological movement into planning. Although annual changes remain extremely small, structures expected to remain operational for many decades may eventually experience cumulative effects resulting from persistent crustal motion. Survey benchmarks established generations ago occasionally require recalibration because the land beneath them has gradually shifted. Even rivers can reflect long-term tectonic deformation. Gentle changes in regional slope influence drainage patterns over geological time. Valleys deepen where uplift accelerates. Floodplains evolve as gradients slowly change. Coastal estuaries adjust to shifting elevations, while sediment deposition responds to subtle alterations in landscape geometry. Volcanoes scattered across the Cascade Range owe their existence to the same plate interaction responsible for the regional tilting. As the Juan de Fuca plate descends into Earth's mantle, water released from the subducting slab lowers the melting temperature of surrounding rocks, generating magma that eventually feeds volcanic systems stretching from Northern California through Oregon and Washington into British Columbia. Although volcanic activity and crustal tilting represent different expressions of subduction, both originate from the same enormous tectonic engine operating beneath the Pacific Northwest. Despite these remarkable discoveries, one recurring phenomenon has captured particular scientific attention because it provides an unusually direct glimpse into the hidden mechanics of the plate boundary. Approximately every 13 to 15 months, much of Cascadia undergoes an event unlike ordinary earthquakes. The crust shifts quietly, almost silently, over periods lasting days or even weeks. Sensitive instruments detect measurable tilting, while most residents remain completely unaware that anything has happened. These events have become one of the most valuable natural laboratories for understanding how stress accumulates and redistributes along one of Earth's most closely monitored subduction zones. Unlike ordinary earthquakes that release energy within seconds through violent shaking, these recurring episodes unfold so gradually that they pass unnoticed by nearly everyone living above them. Scientists refer to the phenomenon as episodic tremor and slip, commonly abbreviated as ETS. Although the movement remains far too small and too slow for people to feel, it has become one of the clearest demonstrations that the Pacific Northwest is continuously changing shape. Every approximately 13 to 15 months, instruments spread across Cascadia begin recording tiny but unmistakable changes in position. The land shifts by only fractions of an inch, equivalent to mere millimeters. Yet those minute movements reveal an extraordinary amount about the forces operating several miles beneath the surface. The discovery of episodic tremor and slip transformed scientific understanding of subduction zones. For generations, researchers assumed that tectonic plates were either locked together, storing stress for future earthquakes, or slipping suddenly during major seismic events. Reality proved considerably more complicated. Deep within the Cascadia Subduction Zone exists an environment where portions of the plate interface move slowly rather than abruptly. Instead of producing destructive seismic waves, these sections gradually creep over periods lasting several days or even a few weeks. Sensitive instruments known as tilt meters first revealed just how dynamic these slow events actually are. Installed securely into stable ground, these devices measure incredibly small changes in the angle of Earth's surface. A tilt so slight that no human could ever perceive it becomes obvious within their continuous records. During an ETS event, the instruments show the landscape gently rocking by minute amounts as the crust responds to movement occurring deep below. Imagine placing a sturdy wooden plank across two supports. Press upward beneath one end while applying downward force beneath another. The board bends slightly rather than remaining perfectly straight. No cracks appear, and the motion remains almost impossible to notice with the naked eye. Yet careful measurements reveal that the board has changed shape. Cascadia behaves similarly. The continental crust flexes elastically, while deep sections of the subduction interface slowly slide, producing broad regional tilting that extends across hundreds of miles. Global positioning system stations confirm the same behavior from another perspective. During these slow slip episodes, stations separated by dozens or even hundreds of miles begin shifting together in recognizable patterns. Some move slightly westward, others eastward, while certain locations experience tiny vertical adjustments. The overall displacement may amount to only a few millimeters, yet the coordinated nature of the movement provides compelling evidence that the crust is responding to large-scale tectonic processes rather than isolated local effects. One remarkable characteristic of these events is their regularity. While the exact timing varies, southern Cascadia commonly experiences major slow slip episodes roughly every 13 to 15 months. That rhythm allows scientists to anticipate periods when monitoring networks deserve especially close attention. Researchers cannot predict the precise day on which an event will begin, but they recognize that the phenomenon recurs with sufficient consistency to reveal an important aspect of plate boundary mechanics. The tremor accompanying these episodes differs fundamentally from ordinary earthquakes. Conventional earthquakes produce sharp seismic waves generated when rocks fracture suddenly along a fault. Tectonic tremor consists instead of prolonged low-frequency seismic signals originating deep within the plate boundary. Individual tremor bursts remain extremely weak, yet collectively they outline the gradual migration of slow slip beneath the Pacific Northwest. As the tremor propagates through the crust, scientists track its movement almost like meteorologists following a weather system across a continent. Clusters of tremor migrate over distances reaching hundreds of miles, equivalent to several hundred kilometers, during the course of a single event. The migration reflects the slow advance of slip along portions of the subduction interface hidden many miles beneath the surface. The relationship between tremor, slow slip, and regional tilting provides one of the most valuable windows into Cascadia's internal behavior. Every event offers another opportunity to observe stress redistribution within the plate boundary without waiting centuries for a major megathrust earthquake. Instead of relying solely upon rare catastrophic events, researchers gain repeated natural experiments occurring approximately once each year. Yet these slow slip episodes do not eliminate the larger tectonic forces acting throughout the region. In fact, they occur primarily within the deeper transition between the locked and freely sliding portions of the subduction interface. Offshore, the shallower section remains largely locked by friction. Farther down, increasing temperature and pressure permit rocks to deform more gradually. The ETS zone occupies the boundary between these contrasting mechanical environments. Understanding that distinction is essential. The deep, slow slip events relieve only a portion of the accumulated tectonic strain. They do not release all of the energy stored along the shallower offshore fault capable of generating enormous megathrust earthquakes. Instead, they demonstrate that different sections of the same plate boundary behave according to different physical conditions. Temperature plays an important role in determining those behaviors. At relatively shallow depths, cooler rocks remain strong and brittle. Friction prevents continuous sliding, allowing stress to accumulate over centuries. At greater depths, elevated temperatures alter the mechanical properties of minerals. Rocks become capable of deforming plastically over long periods instead of fracturing abruptly. Water released from minerals within the descending oceanic plate also influences frictional conditions, further encouraging slow slip within specific depth ranges. Pressure contributes another layer of complexity. The descending Juan de Fuca plate carries seawater trapped within sediments and hydrated minerals acquired during millions of years beneath the Pacific Ocean. As the slab descends into hotter regions of Earth's interior, these minerals gradually release water. Elevated pore fluid pressure within the fault zone reduces the effective friction holding the plates together, encouraging slow movement rather than sudden rupture across certain sections of the interface. The result is a tectonic system exhibiting multiple styles of motion simultaneously. Offshore, one region remains firmly locked. Deeper below the continent, another section repeatedly slips quietly during ETS events. Farther still into the mantle, the plates eventually slide continuously without generating either earthquakes or tremor. The Pacific Northwest, therefore, cannot be understood as a single mechanical system behaving uniformly from top to bottom. Instead, it resembles a layered machine whose components operate according to different physical rules. These differences explain why vertical land movement varies so dramatically across relatively short distances. Coastal uplift reflects elastic strain accumulating above the locked portion of the subduction zone. Inland subsidence develops where the bending geometry changes. Transitional areas experience comparatively little vertical motion because competing forces partially offset one another. Together, these patterns create the broad regional tilt documented by decades of geodetic observations. Even the Olympic Peninsula illustrates this complexity beautifully. Its western margin continues rising at approximately 4 to 5 millimeters each year, equivalent to about 0.16 to 0.20 inches annually, reflecting long-term crustal deformation associated with subduction. Meanwhile, regions surrounding southern Puget Sound display gradual subsidence, indicating that the crust is bending rather than moving uniformly upward. The contrast demonstrates that elevation change alone cannot fully describe tectonic behavior. Scientists must examine the entire deformation field, including horizontal movement, vertical displacement, crustal rotation, strain accumulation, and periodic slow slip episodes. Only by combining all these observations does the larger picture emerge. Satellite geodesy has become one of the most powerful tools for assembling that picture. Hundreds of continuously operating GPS stations communicate with orbiting satellites every day, calculating their positions with astonishing precision. Individual observations may appear insignificant, but millions of measurements collected over decades reveal coherent regional trends that no single survey could detect. Researchers also integrate these observations with satellite radar interferometry, commonly known as INSAR. This technique compares repeated radar images acquired from orbit, allowing scientists to identify subtle changes in Earth's surface over wide areas. Although vegetation, weather conditions, and dense forests sometimes complicate measurements within the Pacific Northwest, radar observations increasingly complement GPS networks by revealing deformation across locations lacking permanent ground instruments. Computational models combine these extensive datasets with laboratory measurements of rock mechanics and realistic representations of fault geometry. Supercomputers simulate how the North American plate responds to the relentless advance of the Juan de Fuca plate. The resulting models reproduce many of the deformation patterns measured across the Pacific Northwest, strengthening confidence that regional tilting arises directly from the mechanics of subduction.